Thank you, Eugenia. Again, my name is Misha, and I'm the and marketing manager here at Quantic Evans in East Providence, Rhode Island. Now, my degree is in electronics engineering, and I've been in the capacitor field in both engineering and sales roles for the last 12 years. And I do have to admit, I am a space enthusiast and have been one since I was a child. I've always been fascinated by the amazing advancements in space that have been made, and I'm thrilled to have the opportunity to play a small part, at least from the capacitor standpoint. So in 1957, we launched our first object into space. Just 12 years later, in 1969, we took our first steps on the moon. In the 70s, satellites for communication and navigation were commonplace. Now this list goes on. Since these early days of the space era, our space-based technologies and capabilities have continued to grow exponentially. Today, we talk of setting up a moon base and sending humans to Mars, and even offering space vacations comparable to the cost of taking your family to Disney World. All of this in 66 years. The exponential growth of these space-based technologies continue today. We rely heavily on our access to space for national defense, to keep us connected, and study our universe, and so much more. As the number of space-based applications continue to grow, they also become more complex. Many of the engineering challenges we face today are much different from those faced during our early years in space. In addition, the tools and electronic components we have at our disposal have significantly improved as well. Now, capacitors play a major role in countless critical space-based systems. These include propulsion, power management, communications, radar, LiDAR, filtering, and so much more. Understanding the best practices for designing capacitors for use in space will provide improved performance and reliability, as well as save space, weight, and power. So the agenda for today's webinar consists of a review of NASA's screening and qualification requirements for spaceflight capacitors, and will highlight important design criteria to consider, including radiation, hermeticity, and derating. Finally, we'll step through a real-life case study comparing capacitor technologies for use in an electric propulsion application requiring high power and a swap-optimized solution. So NASA EEE INST 002 is a great baseline for screening and qualification requirements for spaceflight capacitors. It's available for free on NASA's website. You see it on the link on your screen here. Now, right on their website, it states, the purpose of this document is to establish baseline criteria for selection, screening, qualification, and derating of EEE parts for use on NASA GSFC spaceflight projects, which is Goddard Space Flight Center. Now, this specification actually covers over a dozen components, including resistors, connectors, fuses, magnetics, and switches. Section C1 covers capacitors and breaks it down by tantalum, film, ceramic, mica, and glass, because different capacitor technologies need to meet different requirements to establish reliability. Table 2 in section C1 covers the capacitor screening requirements. Now, 100% of both flight and qualification parts must undergo these screening steps. Now, these steps include visual and mechanical evaluation, along with electrical measurements. Now, these are taken before and after specific tests are performed, just to make sure the parts remain in spec and, of course, intact. Other screening tests include thermal shock, voltage burn-in, fine and gross leak seal test, and that fine and gross leak seal test only really applies to hermetic capacitors. Now, tables 3A through 3E break out the qualification requirements by capacitor type. Qualification testing requires that capacitor samples from the same production lot as the spaceflight capacitors undergo a series of tests in different groups. One example here is Table 3B covers tantalum capacitor qualification requirements. In this test, a specific number of capacitors, the quantity determined by the test failure rate level, as you see on the right-hand side here, must undergo shock, high-frequency vibration, and random vibration testing. These qualification tests are typically based on mill standards. Now, speaking of that failure rate level I just mentioned a moment ago, based on the individual mission requirements, a failure rate level of 1, 2, or 3 is specified. The failure rate level pretty much just sets how many parts must undergo a given test and the minimum number of failed capacitors allowed during that test for the test to be considered passed. Now, taking a look at the requirement we see here, a ceramic capacitor must undergo a voltage temperature limit qualification test. If level 1 is specified, 12 capacitors from the same production lot must be tested, and 1 failure is allowed at the conclusion of the test. If you specify level 2, 6 capacitors from the same production lot as the flight capacitors must be tested, and 1 failure is allowed. If level 3 is specified, this voltage and temperature limit qualification test won't even be required. So INST-002 not only gives users of the capacitors high confidence in their performance, it also gives capacitor manufacturers, such as us, hard targets to design for in meeting the demanding requirements for space. Based on the mission profile, designers sometimes even specify their own tests in addition to specifying the tests seen here in INST-002. Now, there's a clear obstacle that INST-002 adds here: cost. So the additional cost associated with building extra parts for testing and conducting the test adds up quickly. Now, in recent years, launch costs have significantly fallen. So this has been increasing our access to space. We hear in the news, companies like Amazon and SpaceX are putting up thousands of smaller cube satellites into orbit. As these numbers of objects and CubeSats we're putting into orbit increase, the world of commercial space is born. However, there is a cost sensitivity now, different than we've seen in the past when large government or defense projects are putting relatively limited quantities of systems in space. There are few ways to mitigate costs for certain projects without significantly impacting reliability. Rather than a complete screening and qualification, engineers may actually just choose specific tests from INST-002 that align with their mission profile, such as you might drop the life test requirement if it's a short life mission. If a manufacturer, a capacitor manufacturer, can demonstrate ongoing reliability through their space heritage, and this is typically done by naming specific platforms they are on or have been on, an engineer might just choose a screening portion of INST-002 for a given application, since this capacitor has been proven to be used reliably in space. Now, another direction is for other cost-sensitive projects, engineers have used AEC-Q200 qualified capacitors. The AEC-Q200 qualification is a global standard for stress resistance that all passive electronic components must meet if they are intended for use within the automotive industry. Parts are AEC-Q200 qualified if they pass the aggressive set of tests contained within the standard. Now, despite the fact that going this route, space flight capacitors aren't specifically screened, oftentimes the higher level assembly that the capacitor is integrated into does undergo a screening. So that screening might be sufficient in establishing a comfortable level of reliability. And obviously, we need to keep our reliability engineers on the project happy as well. So let's move on from testing and reliability, and let's take a look at specific design criteria for capacitor selection. In order to withstand the vacuum of space, a hermetically sealed capacitor may be required. Although hermetic is commonly thought of as meaning airtight, it really means that gases and moisture can't penetrate or escape the capacitor. In some cases, the capacitor may be used within a hermetic enclosure, like the illustration we're seeing here. In those cases, an engineer might be able to relax their hermeticity requirements. So Earth's magnetic field shields us here on the ground from radiation from sources such as cosmic rays and solar particle events. But in space, our electronics are fully exposed. For some capacitors, high levels of radiation can and will impact performance or might even cause damage. There are capacitors that do carry a radiation hardened or rad hard, as we refer to it, designation. This just means that the capacitor is able to function as intended in the presence of radiation. If the capacitor that we choose is not rad hard, a designer may have to implement some sort of shielding solution. So during launch, capacitors are subject to high vibration conditions. In addition, a deployment event such as the one we're seeing on the bottom right hand side of the screen can create a high shock condition. So we need to ensure that the capacitor is rugged enough to withstand these conditions, as well as ensuring the capacitor is mounted to the circuit in a way that protects it from damage during these high shock and vibration events. Now, capacitor performance typically varies as conditions change. So it's very important to understand how the capacitor performs in these varying conditions. Taking one of our capacitors as an example, at low temperatures, as you see on the graphs here, the capacitor's ESR is higher. This can be of particular note if the mission has a cold start condition. Under these circumstances, the circuit needs to be designed to accommodate this higher ESR at lower temperatures. On the other side, as temperature rises, the capacitance increases. So designers should be sure to ask manufacturers for ESR versus temperature or capacitor versus temperature curves, such as the ones you see on this page, as the circuit analysis is performed. There are several aspects to a capacitor's life that come into play. Some defense applications may sit dormant for years, and when they're used are very short in operating life. Deep space missions typically take several years before the capacitor is energized and in use. Designers must consider the storage life of the capacitor in order to assure it's ready for use once it's needed. There are capacitors that are limited in storage life, and some capacitors actually have an unlimited storage life. So another aspect of the life is the operational life. How the capacitor is used during the mission and the environment it is subject to will determine its estimated operating life. For example, one of our hybrid tantalum capacitors, has a baseline life rating of 2,000 hours when used at its rated voltage and its rated temperature of 85 degrees C. Designers can increase this life by derating the capacitor. For reliability purposes, you need to derate a capacitor anyways. In the case of Evans capacitor, there's an approximate doubling of life for every 10 degrees C reduction in operating temperature from that 85 degrees C rated temperature. And there's another approximate doubling of life for every 10% below the rated voltage in which the capacitor is used. In many space applications, 50 to 60% voltage derate is very common. Now, despite our best efforts, we can do everything right, but failure still can occur. Oftentimes, usually, redundancy is designed into the system to mitigate the risk of failure. However, the way the capacitor fails should be something to keep an eye on. Solid tantalum capacitors are routinely used in space. But when they fail, they have the potential to fail open, and they also have the potential to fail catastrophically by catching fire, as you see on the image on the page. This scenario can create a domino effect and lead to a catastrophic overall system failure. Choosing capacitors that fail in a less dramatic fashion, such as capacitors that fail open, allow failures to be contained. Otherwise, the system needs to be designed in a way to mitigate these potential failure modes, again, like the image that we see on the screen. We hear of swap savings all the time. Swap or space, weight, and power savings. It's one of the biggest design criteria in engineering. As it pertains to space, the larger and heavier the capacitor, the more expensive it is to launch. For higher power requirements, using several capacitors connected in series parallel configurations hurt reliability, because the more components that we use, the more opportunity there is for failure. Being mindful of options for swap optimized capacitors contributes to the size and weight of the capacitor solution. Let's step through a real-life case study and compare some options. A design engineer has a space-based application, and after doing all of his calculations, he or she determines that they need a 63-volt, 8,900 microfarad capacitor. An aluminum polymer capacitor solution is evaluated to meet this need. One solution that this engineer considered is Chemet's PHA226 series. One capacitor within the series is rated at 63 volts and 560 microfarads per capacitor. So in order to meet the 8,900 microfarad capacitor, the capacitance requirement, this designer needs 16 capacitors connected in parallel. This would consume a volume of 12.64 cubic inches and weigh in at about 320 grams. Another solution for consideration would be one of ours, a Quantic Evans TDD series capacitor. These hybrid wet tantalum capacitors have a very long space heritage and are well suited to meet the demanding environments of space. One capacitor within the series has a rating of 63 volts and 9,400 microfarads, and they routinely pass the screening and qualification requirements as specified in NASA's INST 002. The Quantic Evans solution consumes a total volume of 0.9 cubic inches and weighs in at 86 grams. So we actually provide a significant volumetric and weight savings compared to our aluminum polymer solution. So that brings me to the end of the webinar. Thank you so much for participating and listening in. There's a white paper that focuses on this topic, and it's available via the QR code in the invitation or in the resources section of our website, quanticevans.com. If you have any questions or wish to further discuss your application, please feel free to reach out to me.
Thank you very much for the presentation. And just a reminder for the audience, in order to ask questions, you can send them via the Ask a Question widget. Just type them into the box and click Submit. Please note that you can still send your questions after the webinar, and they will be answered at a later date. Okay, and it looks like we've got several questions already. So our first question is, how long does the testing and qualification for NASA INST 002 typically take?
A great question. It does vary by manufacturer because, of course, you have the lead time to build a capacitor, and then you have to run the battery of tests. However, the longest portion of that test is the life test. There's a 2,000-hour life test that's located within INST 002. That typically is the longest portion of that standard. So between the capacitor's lead time, the 2,000-hour life test, and giving the manufacturer an opportunity to write up a report. You can, if you want the full INST 002 qualification, you're looking at over 3 months at the earliest.
Okay, thank you. And our next question is, what are the key differences between AAC Q200 and INST 002 as it pertains to reliability?
Yeah, great question. So the AEC Q200 really qualifies the capacitor's design. It doesn't qualify the capacitor, unlike INST 002 does. So you do have an impact to reliability when you're just going with the AEC Q200 qualified capacitor for use in the space application. But the testing is really, really stringent. The quality requirements is really stringent. The automotive industry has done a pretty thorough job of making sure that these capacitors are extremely robust. And obviously INST takes it to another step because the specific capacitor being put in flight has to undergo that screening test, and you have that level of confidence from the qualification test as well.
Okay, thank you. And the next question is, how does your company, Quantic Evans, participate in space?
Oh, yes, excellent question. So we make hybrid wet tantalum capacitors. They come in a tantalum case, so they are rad hardened, of course. They're hermetically sealed, and we work on a variety of defense applications, electric propulsion applications, and space-based radar systems, space-based lidar systems, power management systems, and we're used on a few NASA projects, and a lot of the defense projects, of course, we're not able to find out the exact use, but we know we're in orbit in a number of different applications there. So we do have quite a bit of experience in designing and getting capacitors up there for space too.
Okay, perfect. And our next question, what types of information is typically asked of capacitor manufacturers by engineers looking to use a capacitor in space?
Yeah, another good one. So we typically, space heritage is one of the biggest ones. So before the conversation happens, the first thing is this capacitor space grade? Yes. The next question is, what platforms are you currently in service on? That can be tricky, especially in the defense world, divulging that kind of information. But usually there's some, NASA government-funded projects that are more needed for the public domain or used in the public domain there. And then after that, a lot of the things that we talked about in the presentation, and really have we dealt with the NASA INST 002 before and things of that nature. So it's really about, is this classified as space grade? And are you familiar with INST 002 alongside your space heritage?
Okay, perfect. And the next question is, does Quantic Evans develop high voltage capacitors up to 800 VDC to 1000 VDC?
Unfortunately not. So the technology we use, our sweet spot is the low to medium voltage range, 10 volts to 125 volts. Now, we do have capacitor module assemblies. They can be found right on our website, where you can bank several capacitors within one enclosure and you can connect them in series to get to higher voltage levels. Of course, there's a sweet spot. So I think 1,000 VDC. That's might be outside of our sweet spot. I would love the opportunity, though, to kind of speak one-on-one to see if our capacitors would be right for that particular application. But just to reiterate, any single Evans capacitor, the maximum voltage rating we offer in any single capacitor is 125 volts. And then we have to bank them together to get to higher voltages, which we do for a variety of customers.
Okay, thank you very much. And okay, we have one more question today, which is, are the slides going to be shared?
Absolutely. Great.
Yeah, perfect. Thank you very much, everyone. Just a reminder for the audience, you can still send any questions while watching on demand. All questions will be answered at a later date. I would like to thank Misha for the presentation and Quantic Evans for sponsoring this session.